In the early 1990s, two rival teams of astronomers entered a race, one that would shake the foundations of everything we thought we knew. Their goal? Nothing less than understanding the fate of the universe. Using telescopes around the world, including the Cerro Tololo Observatory high in the Chilean Andes, they believed that by observing just one thing, they could unlock the secrets of how the universe was born and where it was heading.
By watching a star die.
But this wasn't just any star. It was a white dwarf. White dwarfs are stars in the final stage of their lives. When a star similar to our sun exhausts its nuclear fuel, it first becomes a red giant. At this stage, the massively expanded star collapses inward as it becomes a white dwarf.
The helium surrounding the star becomes extremely compressed until it reaches a breaking point and explodes. In this explosion, most of the star's mass is scattered into space, and what remains, mostly the core, is what we call a white dwarf. But the white dwarf these astronomers were watching had a neighbor, a young star. This young star transfers some of its mass to the nearby white dwarf, and at a certain point, the white dwarf's mass reaches a critical threshold, and it explodes.
We call this a Type 1a supernova.
Astronomers' favorite type. Because they are all nearly identical, and through the same physical processes, they put on a spectacular show. But here's the problem. These supernovae are incredibly rare events. The last supernova observed in our galaxy happened over 400 years ago. First spotted on October 9, 1604, this brilliant new star in the sky was studied extensively by Johannes Kepler, who observed it for months and wrote an entire book about it. That's why we call the last supernova observed in our galaxy Kepler's supernova, technically designated SN 1604.
That's exactly why, when Betelgeuse started showing signs of an imminent explosion, the entire scientific world went absolutely wild. Every telescope on Earth turned toward the heavens.
But then we learned that Betelgeuse wasn't actually going to explode. We were disappointed, but there was nothing we could do about it. And so, the astronomer teams I mentioned at the beginning turned their gaze to other galaxies, because according to the latest estimates, the observable universe contains over 2 trillion galaxies. 2 trillion! In a galaxy like ours, a supernova occurs roughly once every 100 years. So these astronomers use massive telescopes to scan tens of thousands of galaxies, essentially going on supernova hunts. Supernova hunting. Now that would make one heck of a job title. And there's another challenge. It has to be a Type 1a supernova specifically. Not just any supernova will do. And so the astronomers I've been telling you about spent years hunting these specific supernovae, calculating their ages and using comparative analysis to try to solve the mystery of the universe's expansion. The universe was expanding, but that expansion had to stop somewhere. Because, as you may remember from our previous video, Vera Rubin had recently detected dark matter, and the gravitational effect of this dark matter, hidden in what we thought was empty space, was an undeniable reality. The gravitational pull of this dark matter would surely one day halt the expansion. Eventually, the expansion would stop and the collapse would begin. But the results of these astronomers' work would deliver a shock that no one saw coming. Dark matter, combined with all the ordinary matter we knew about, was incredibly powerful. It should have been enough to stop the expansion. But despite all that matter, and even more dark matter, there was a massive problem.
Every single finding pointed to one conclusion. The expansion of the universe wasn't just failing to slow down, it was accelerating.
Despite all that gravitational pull, the universe was accelerating faster and faster with each passing day.
It was as if something else was out there, creating an anti-gravity effect, a force that pushed matter apart, that repelled everything trying to hold together, a force that grew stronger and stronger, accelerating everything away from everything else, tearing the universe apart.
The rival astronomer teams I mentioned at the beginning reached the same conclusion at the same time. And at a certain point, both groups decided to come together and discuss this incredible phenomenon, because all the data pointed in the same direction.
But now, hold on tight, because an old friend is about to enter the stage.
When both teams announced their findings simultaneously at a conference, the audience was stunned. They were witnessing a brand new scientific discovery.
Something entirely new. Something never seen before. Never heard of before. But one man, a very long time ago, back in 1917, had already said something about this.
And in 1931, he would come to deeply regret what he had written, calling it his greatest blunder.
Who was this man? Of course, our old friend Albert Einstein.
And behind dark energy, there he is again. In 1917, he would add a constant to his field equations. He called it the cosmological constant and represented it with the capital Greek letter lambda.
And the purpose was this: there had to be a force standing against what we call the Big Crunch, the scenario where gravity would cause the universe to collapse in on itself. According to Einstein, the universe needed to be in perfect equilibrium, neither expanding nor contracting.
And this, according to Einstein himself, would become his greatest mistake.
Because in 1929, Edwin Hubble had discovered that the universe wasn't static at all, it was expanding. And with that, Einstein removed the cosmological constant from his field equations.
Until 1998, after the astronomers I mentioned at the beginning proved that the universe's expansion was accelerating, and after they received the Nobel Prize in Physics in 2011 for this discovery, Einstein's so-called greatest blunder, the cosmological constant, came roaring back. And what became clear was this. Einstein had indeed found the cosmological constant, but he wasn't entirely sure why it worked. His general relativity equations actually predicted that the universe should be expanding. To prevent the universe from eventually collapsing under its own gravity, he introduced a mathematical constant that gave the very fabric of space-time itself a tendency to expand. The idea behind the cosmological constant is actually simple. The fabric of space itself contains a non-zero energy. This is the simplest way to explain dark energy. It arises purely from the properties of space itself.
But here was Einstein's problem. When he proposed all of this in 1917, he didn't even know the universe was expanding. And yet, he had foreseen it. His idea was truly wild for its time.
He had already revolutionized physics more than enough with general and special relativity. Perhaps he didn't want to provoke even more controversy by claiming the universe was expanding.
And so, in 1931, after the expansion of the universe was confirmed, Einstein concluded that his balancing constant was unnecessary, and he discarded it. The old Einstein had essentially thrown the young Einstein's theory in the trash.
But it would take decades upon decades before the young Einstein was proven right.
Without this constant, the assumption was that the universe was expanding at a steady rate. But when it turned out the universe was actually accelerating, well, that changed absolutely everything. Now, let's recap. The astronomers studying all these supernova, some dating back 11 billion years, and analyzing their redshift, the shifting of light toward the red end of the spectrum, discovered something remarkable. Up until about 5 billion years ago, the universe was expanding in a way that suggested it would slow down, stop, and eventually collapse. But then, 5 billion years ago, a critical threshold was crossed, and the universe suddenly began accelerating. And here's the explanation. The gravitational pull of dark matter and normal matter was quite strong up to that critical threshold. But as the universe expanded, gravity's grip weakened. Here's a fundamental fact. When you double the distance, gravity weakens by a factor of 4. The farther apart things get, the weaker it becomes, and it just keeps getting weaker. At that point, 5 billion years ago, dark matter and normal matter essentially gave up. They were defeated by something darker and far more mysterious. Dark energy. Because as gravity weakens, this dark force, called anti-gravity, grows exponentially stronger. Think of it as if one is draining the other's power. It might sound crazy, but here's one way to think about it. Imagine two galaxies moving apart. As the distance between them grows, more and more dark energy appears in that gap. The more space there is, the more energy there is. A nothingness that grows ever more powerful. But here's the real question. Does nothingness even exist? That's exactly what Einstein's constant was about. It spoke of the energy of nothingness, a force that opposes gravity, the power of nothing. The young Einstein hadn't made a mistake. What Einstein called his greatest blunder may have actually been one of his greatest discoveries. The young Einstein had discovered the power of nothing. Isn't that incredible? I mean, how does a person manage to be right, even about something everyone thought he was wrong about? It's just incredible. Anyway, where were we? Ah, yes, the power of nothingness. But what does quantum physics tell us? There's no such thing as nothing. That's right. There is no such thing as nothing. No true emptiness. Particles are everywhere. We can see some of them, and others, we don't even know they exist. We don't even know what we don't know. Do you feel it too? We really don't know anything. At least that's what I think. There's so much left to learn. Right now, there are two forces at work in the universe, one holding everything together, and the other pushing everything apart faster and faster. And we have no idea what either of them really is. And get this, let me tell you something even wilder. Think about the Big Bang, the Great Explosion. When we think about it, we picture a single explosion, right? But here's something we're nearly certain of. We have no evidence that there was only one Big Bang. Alongside the Big Bang that created our universe, there could have been thousands, millions, even billions of other explosions. For galaxies, we might be living in just one of billions of other universes. And maybe in those universes, there are other people. Let's indulge in a little imagination. Your counterparts in other universes, other versions of you having this very same conversation, another you watching this exact video right now. But let's pause here for now. There is so much more to explore, but I'm sure you get the idea. Soon we'll dive into the multiverse, just one of countless topics waiting for us to discuss.
So don't forget to turn on notifications.
And once again, I want to thank all the supporters. Your support truly means so much. I'm looking forward to your support as well. If you share this channel and what we discuss here with the people around you and share from your accounts,
That would mean the world to me.
And as always, until we meet again, I'm glad you're here. Take care.